in Zoom land in here. My name is Paul Spence. It is my great pleasure to introduce Madi Rosevear, who's giving the talk today. Madi has a passion for GFD, she tells me, in particular how it relates to the ocean. And she really likes learning about small-scale turbulence and how it interacts with ice shelves. She did her PhD in 2020 at UTAS on ice-ocean boundary layer processes. She did a brief postdoc at UWA, and then is now doing a postdoc at the University of Melbourne, as you can tell. Tomorrow is her birthday. And what I really know about Madi is that she's very smart. She's very friendly. She generally seems quite happy. And she's very adventurous. And I'm grateful to have her sitting outside of her sitting near me, and she's not allowed to move. That's it. Thank you.
Okay, well, now she's very embarrassed. So, yeah, thanks, Paul, for the introduction, and thanks everyone for coming in person and online. That's great to see so many people. So today I'm going to be talking about basal melting of Antarctic ice shelves. So this is sort of an ocean-driven process. So I'm going to start by showing you what makes the ocean beneath an ice shelf interesting and unique, and then I'm going to cover some of my own work on the processes controlling basal melting. So fundamentally, these are turbulent processes, but I was smart enough not to put that into the title and scare everyone away. But yes, so hopefully there's something easy for everyone. I thought I'd make sure we're starting from the same point. I mean, I know this is ACEAS and we know about the ice sheet, but this is a schematic of the Antarctic ice sheet, and you can see that we are accumulating snow in the middle, which is turning into ice, and then it's sort of flowing outwards under its own weight, and at some point it's reaching the ocean, and it goes afloat, and we get this floating tongue, which is our ice shelf. And then so the ocean cavity is sort of the ocean beneath this ice shelf, and then basal melting is the ocean-driven melting on the underside of this ice region. So why are we interested in basal melting? I guess firstly for ice sheet stability and sea level rise. So this is a nice figure which I think illustrates this process quite well. So we're looking down on Antarctica and we can see the ice sheet, and then the ice shelves are coloured in this gold and blue. So what the colour is showing us is the degree to which these different ice shelves are restraining or buttressing the flow of the grounded ice into the ocean. So basically anywhere where you see the gold or the warmer colours, the ice shelves are doing a lot of work to hold back the grounded ice, and if we were to thin those ice shelves or if they collapsed, we would expect the grounded ice, the flow of the grounded ice to accelerate, drain into the ocean more, and we would see more sea level rise. The other reason that we're interested in basal melting is because it determines the properties of the water masses that exit these ice shelf cavities, and that has sort of flow-on effects for shelf circulation and also the formation of important water masses. So yeah, this figure is from Ruth Morgan's paper, and it's a perturbation experiment. So what they did was increase the amount of basal meltwater coming from the ice shelves, and showed how that changed circulation on the continental shelf, and that it also altered the formation of Antarctic bottom water, which is a really important component of the global circulation. So I guess basal melting is important, but I wanted to also give you a bit of a picture of what's unique and what I find interesting about the ocean within these ice shelf cavities. So this is another top-down picture, and I guess the first thing I wanted to point out is that these ice shelves, which are sort of again with this red-blue kind of color map, they're often constrained by land, so they're embayed. They're really, really wide and long, so hundreds of kilometres, and really thick, so sort of up to 2 kilometres thick. And so these two things sort of conspire, along with the difficulty of getting to Antarctica, which we all know about, to mean that the ocean beneath these ice shelves is really poorly sampled. Like we're lucky to have 1 or 2 measurements beneath, you know, any one of them. So a very badly constrained system. Yeah, we can also see here the continental shelf in this kind of greeny blue color map, which is showing us the ocean temperature relative to freezing. So you can see that there's quite the range from temperatures that are close to the surface freezing point to temperatures that are about 4 degrees above it. And in a conventional sort of ocean setting, that might not seem like that much variation, but it does turn out to be a lot in the context of melting and the circulation that it drives in the cavities. So you can see that those really warm areas, like the Amundsen and Bellingshausen seas, sort of coincide with the really rapid melt rates. But yeah, also that other shelves like the Amory Ice Shelf, which has long been a focus of the Australian program, like the temperatures out the front of the Amory are quite cold, but because it's one of those really deep ice shelf cavities, we can get really high melting at depth. All right, another difference to sort of conventional oceanography, I guess, is that the oceans in these cavities are insulated from direct forcing by the wind, but they're subject to this really strong buoyancy forcing because of the melting and freezing and just thermodynamic interaction with the ice shelf. And yeah, so by buoyancy forcing, what am I talking about? Well, the meltwater is fresher and therefore lighter or less dense than the ambient ocean, and so that can drive circulation. So that's what I'm showing with this schematic. So we have, let's get my cursor to catch up. Yeah, we have some water mass flowing in along the seabed to the very base of the ice shelf. It's driving elevated melting and forming some buoyant meltwater, which is then sort of flowing back out towards the open ocean. So this is a very simplified view, but yeah, just I guess to say that you know, the presence of meltwater, you know, is a really important driver for the circulation as well. Yeah, this leads to an upside down temperature structure. So we have typically the cold water at the top in the polar regions, which is unconventional as well. And in terms of the cavity environment in general, there's a huge range of sort of, I guess, flow conditions that we observe, from really like calm and quiescent to very energetic. And the types of circulation that we observe are sort of tidal flows, that plume circulation that I just described, and other things like gyres and eddies that make their way into the cavity. I wanted to give 2 kind of examples of different environmental regimes, I guess. So these are some observations from beneath the Larsen Sea ice shelf, which is sort of on this Weddell Sea side, and it's quite cold. So these up here, we're looking at the flow speeds beneath the ice shelf over a year or so. And I guess you can see that the currents are really dominated by tides with sort of flow speeds up to 20 centimeters per second. And the conditions are really cold. So coldest water at the top, like we described before, and the temperatures here are only 0.05 above the local freezing temperature. And consequently, the melting is quite weak, so less than a meter per year. And our kind of counter example is Pine Island Glacier ice shelf. So this is a warm cavity. And then again, these are observations from within the cavity. So the current speed now is relatively fast, but it's steady. So this isn't a tidal flow. This is more like a plume that's running along the base of the ice shelf. And then the temperatures here are about 1.5 degrees above the local freezing temperature. And so we get quite rapid melting here of 15 meters per year. So I wanted to recap at this stage just to say that we're interested in basal melting because it affects these important things, so ice sheet stability and sea level, and then also circulation and formation of various water masses. And there really are a wide range of conditions that we observe beneath ice shelves. And what that means is, I guess we need to understand quite a wide range of processes in order to predict basal melting. And so it's those processes that I'm going to be talking about mainly. Okay, that's maybe my water point. Yeah, so what I'll talk about for the rest of the talk, and because it's been the focus of my work, is the ice shelf ocean boundary layer. So I'm attempting to illustrate it here. So this is our cavity overall, and then we're zooming in sort of right next to the ice. And the boundary layer is this narrow turbulent layer, which is really important because it controls the transport of heat and salt to the ice and determines how quickly the ice shelf melts. So I guess the overall scale of this thing is kind of 10 meters, but within it, we actually have to care about millimeter scale processes right next to the ice. So yeah, the upshot, I guess, is that globally relevant quantities like our melting and our ice shelf water formation depend upon this really narrow boundary layer. And there's a couple of types, I guess, of it. So we talked about the role of buoyancy and buoyant meltwater. So in this scenario, we have kind of a sloping ice shelf, and that buoyancy is driving flow next to the ice and generating turbulence. And it's this mechanism that is responsible for setting the melt rate, basically. And some people have done a lot of work on this, and they're not me. So I've been working on kind of a different problem. So like we saw before in other areas, tidal flows or other steady currents are quite important, and the ice shelf can be quite flat. And in this scenario, we have our ice shelf and we have some flow beneath it, and friction between the ocean and the ice is generating turbulence, and that turbulence is mixing heat upwards and eventually setting the melt rate. So that's the scenario I'm going to be talking about today. So just to, I guess, motivate the why a little more, all of these things, I guess, the scales that we're talking about are very small. And so it means that these are not processes that are included currently in sort of ocean and GCM type models. They're all subgrid scale, we would say, so they operate on much smaller scales than the model grid size. So that means we need some way to represent the effect of them in this model without actually explicitly including them. And so that's where a parameterization comes in. And so, oh yeah, I guess this is just a grid. Okay, I think there was one last thing I would say about this. All right, no, we'll call it done. Okay, so my approach was to run high resolution models of just this boundary layer region using a technique called large eddy simulation, which I won't go into, but feel free to ask me about it. So we have this really idealized model domain. So that's what I'm showing here on the right. So we have our ice-ocean interface at the top, and then we have kind of a cube of ocean beneath it. And we're forcing some steady flow in that ocean. So this green is supposed to be showing you the velocity profile. It's stratified, and up top we have a special boundary condition that simulates the melting. And what we do with this idealized domain is we vary the temperature and the current speed in order to determine how melting responds to these different conditions, and also like how the boundary layer profile and properties change. And to give you an idea of the physical scale, this is 10 by 10 by 20 meters, this model domain. So I'll describe these fields on the next slide. So I'm going to start with this cold energetic conditions. It's actually one of the last things I did on this problem, but it's sort of the simplest case to understand. So as I said, cold energetic conditions. So parts of the Filchneroni or the Ross ice shelf might look something like this. And so what we're looking at here on this vertical plane, this is the temperature field. So you can see, again, we have the cold stuff at the top, and we formed this turbulent boundary layer. You can see the turbulence here. This is the vertical velocity, so you can see these overturning eddies. And then this is the melt rate and the top surface. So you can see one of the interesting things about this is it's spatially quite variable. So it's sort of reflecting the turbulence within the boundary layer, which is kind of neat. So here we're looking at sort of how the experiment evolves over time. So this is the melt rate in the black colouring, and so that's evolving over sort of a period of a few days. So you can see it takes some time to sort of spin up, and then we get this quite nice steady melt rate. And that steady melt rate, it turns out, is related to something that we call the friction velocity. So this could think of as a scale of our turbulent eddies within the boundary layer. Sure there was a point to that box appearing. Oh yeah, I guess, yeah. So this is the period where of observing a steady melt rate. It's decreasing very slightly over time, and if we look at the temperature field, we can sort of understand that. So this is how the temperature, so what we're looking at on this panel, this is how this is evolving over the whole experiment if we take the horizontal average over this model domain that I'm showing you. So what you can see is we kind of initially form this mixed layer, and then over time it's gradually deepening, and it's also gradually cooling and freshening, and that's in response to the fact that we're adding melt water. So you can see that, our melt rate is decreasing over time, but that's just in response to the fact that the mixed layer here is a little bit cooler. If we look at the turbulence, so this field is the turbulent kinetic energy. We see that that's kind of nice and steady over time as well. So I guess overall we find that this boundary layer region is well mixed. And even though we're adding this buoyant meltwater at the surface, we find that it's not really affecting the turbulence beneath the ice. So we get this relationship between melting, our steady friction velocity, which I showed before, and then something that we call the thermal driving. So that's the difference between the local temperature and the in situ freezing temperature. So that's that TF. So it sort of tells us about the heat that's available for melting. And so the nice thing about this, I guess, is this is the expression that's kind of used in the literature and in ocean models, I should say, at the moment to represent melting. And so under these cold and quite energetic conditions, we find that it works really well, which is nice. Did I go back in time? Sorry.
Could you just go through that equation that works so well for me?
Oh, okay. Well, yes. Sorry. So this is melt rate, and I'm just saying that it's proportional to some constant here, which this is called a transfer coefficient, and we'll talk about it a bit more later. And then multiplied with by the friction velocity. So that's a measure of our turbulence intensity, and then the thermal driving, so the elevation of the local temperature above freezing. So yeah, when we're in really cold and energetic conditions, we find that the value of this gamma seems to be kind of constant over a range of conditions, and it's quite high, I guess. That's in a relative sense, but that should make a bit more sense later. All right, but we want to try and understand warmer and more energetic conditions. Warmer conditions, but still in situations that are, I guess, relatively energetic. And so in order to look at this, we sort of started ramping up the temperature. And so what you can see when we do this, because the only thing that we change between these two experiments is increasing the temperature, so the flow speed is the same. We find that overall, there we go, we get a thinner mixing layer and the turbulence is less intense within our boundary layer. So this is something that we wanted to, I guess, try and quantify. All right. Ooh. Let's see. We'll just go on. Okay. So here we're contrasting those two cases. So this is the first case that we looked at before. This is that cold and energetic scenario where we have this well-mixed boundary layer. And then on the right-hand side, this case corresponds to our warmer case, which is what we see here. So in the top panel, you can see that over time, the turbulence is sort of dropping off. And also the stratification is building up near the ice. So you can see that initially we did some mixing and we had our mixed layer, but over time, because of that buoyant meltwater being continuously added, the mixing depth started to drop off and we formed sort of this second picnic line beneath the ice. Sorry, I should have said initially that we're looking here at the buoyancy frequency. So this is a measure of the stratification of the water column. So I guess our general statement about this is that buoyancy, and that's our buoyant meltwater, is suppressing the turbulence and thinning the mixing layer in this scenario. And what that means is that overall, the stratification is stronger near the ice and the ice is insulated from the warmer water below. Because remember, we've got that upside down stratification. So the upside down temperature profile. So the warmer water is at depth. And so the fact that we're not mixing as deeply means that we're not supplying as much heat for melting. So we sort of see a second effect because of buoyancy, and this is sort of relates to the equation that Paul was just asking about. So this is our what's happening to our transfer coefficient over time. So this, just bring all this up, make it a little bit easier. So this was the expression we had before that worked quite well, where we found that our melting was related to the friction velocity, the temperature, and then this transfer coefficient. But what we found is as we increase the temperature, this transfer coefficient started to decrease. So what that means is that the heat and salt transport to the ice are essentially becoming less efficient. So we have plenty of heat available for melting, but our melt rate isn't going to be as high as we, I guess, would have anticipated based on our original results where this gamma-T was constant. And so the interesting thing about this is that, I guess, this falls outside of what's currently represented in ocean models. And it sort of represents a feedback whereby if we increase the temperature, we increase the melt rate, that in turn suppresses the turbulence and decreases the melt rate. So it's this interesting negative feedback. I wanted to do a bit of a primer, which in hindsight probably could have come before that, on the effects of stratification on turbulence. And I hope that everyone's okay and not too upset that I'm talking about this. But in essence, what we've got happening beneath our ice is sort of a competition between the turbulence, which, as I said, is generated by far-field flow, which is trying to mix up the temperature and salinity and make it homogeneous, and buoyancy, which is really trying to stratify the water column and leave us in this situation where we have cold water at the top and warm water at the bottom, and it's quite strongly stratified. And I guess if the stratification becomes strong enough, it can totally suppress the turbulence. So that's very important from our perspective of trying to understand the melting, because this will really decrease the amount of heat available for melting. So we want to know how to, I guess, assess the degree to which stratification will affect our problem and will affect our ice ocean boundary layer. And I guess luckily for us, there's a pretty good analog for this system in the atmospheric literature. So as with lots of things in oceanography, yeah, the atmospheric people were pretty onto it. And so analog, I guess, is the nighttime atmospheric boundary layer where it's quite well stratified. And so in order to, I guess, understand the degree to which stratification will affect our boundary layer, we're going to compare two different quantities. So one's the buoyancy flux, so the rate of buoyancy transport due to melting, and then the other one is the turbulence production. So our buoyancy flux on the left, and then our turbulence production for a boundary layer on the right. And we're going to rearrange these two so we can have a length scale. And what this length scale is telling us is how big does my eddy have to be before it will feel the effects of stratification. Because really small scale motion won't feel the effect of stratification. As we get to bigger turbulent scales, we start to feel the effect of stratification. But I guess for this length scale to be meaningful, we need something to compare it to. Oh, it's called the Oberkopf length scale, if anybody would like to use it in their work. So the first thing we're going to compare it to is the overall size of our boundary layer. And we have this neat expression to predict that. And then the second thing we're going to compare it to is a much smaller scale. So I said before that we cared about millimeter scales right next to the ice. And I haven't sort of delved into that too much, but we have another scale that we can compare our Oberkopf length scale to, which is a sub-layer scale, and that's the expression for this down here. So by combining these two different scales, we can get two different parameters, because we like combined scales. And so one's our stability parameter, and this is our viscous Oberkopf scale. And yeah, I feel like this one is a nicer name, but anyway. So do our new parameters help us quantify those effects that we're describing, right? Because I was sort of giving you a bit of a qualitative idea of how stratification and how meltwater was sort of feeding back on our boundary layer and on melting. So the answer is yes. So up here at the top, we have a nice predictive model, which I haven't and won't go into, for predicting the depth of this mixing layer on the left. And all these sort of circles, those are conditions where we don't observe the stratifying behavior. And then all these squares down here, sorry, I keep losing my cursor. All these squares down here, these are where we do observe the stratifying behavior that I described. So basically, we have this original model for well mixed conditions, and it works for well mixed conditions. So these dots fall on our line, but it doesn't really work for our stratified conditions. So if we try and draw in that stability parameter that I just described, we get this other relationship, and we have a nice sort of model, empirical model to predict the mixing layer depth when buoyancy is really affecting turbulence near the ice. So not only does it tell us what the depth of the layer will be, it also tells us when we should expect stratification to become important. So once this parameter gets above 1-ish for our flow, we start to be in this stratified regime, as I've been calling it. And so just to recall, I guess, that this parameter was looking at the Oberkopf length scale and saying, well, this is how big an eddy has to be affected by stratification. And then it's looking at our overall boundary layer scale, which is our biggest possible eddy. And so if the ratio of those two is 1, we are starting to be affected by the stratification. So that kind of makes intuitive sense of that, as well as working quite nicely. Okay. Oh, this was denser than I realized when I put it together. Apologies, everyone. Okay, so right, but we have our second scale, and we want to know if that can help us describe.
Just line plots.
No problem.
Yeah, there's not really any math. All right, so now we're looking at the transfer coefficient. So again, this was describing the efficiency of heat transport to the ice. And we found that that was dropping off as temperatures warmed up and as increasingly we are feeling the effects of dumping a lot of meltwater just at the top of the water column. So yeah, if we plot this parameter as a function of our other scale, so this is our viscous Oberhof scale, we find that we can explain the variation in this parameter. And this is just sort of an empirical fit to what we're seeing. But yeah, what's happening on the end to the left is that turbulence really close to the ice is being suppressed. And this is actually not just stratification, but also the effects of viscosity, which we don't have to talk more about. And then on the right-hand side, turbulence close to the ice is not being affected by stratification. So I guess one of the interesting things about this is that we have to use a different parameter to describe the effects of stratification on melting, because melting is governed by processes really close to the ice, as compared to before, when we had to use a slightly different scale, which also involved our Oberhof length scale, but in a slightly different way, to describe the effects of stratification on the boundary layer overall, which is quite an interesting result. Okay, so key points so far. I think it gets lighter from here on out. We discussed those. Beneath the ice, turbulence and buoyancy are in competition. So one's trying to mix the water column and the other is trying to stratify. Under cold and energetic conditions, we find that the meltwater isn't really affecting the environment beneath the ice shelf. So we get this efficient heat transport to the ice and kind of a thick energetic boundary layer. But once we start moving to warmer conditions, buoyancy is now thinning and stratifying beneath the ice and having this insulating effect where there's not so much heat available for melting. Secondly, the buoyancy is reducing the efficiency of the heat transport to the ice. So it's this kind of double whammy in terms of both these things acting to decrease melting. Yes. Okay.
It's a good thing.
It's a good thing.
Good thing.
Yeah, but there's some caveats which we can get to. Yeah, it's a good thing. All right, so yes, this is Curious George, by which I mean curious observations beneath George VI ice shelf. So these are some temperature and salinity profiles from beneath George VI, which is a kind of a warm cavity. So this is depth on the left-hand side, and we're looking at temperature here and salinity on the right-hand side. So what you're seeing here is really well-mixed layers in both temperature and salinity, separated by these sharp gradients. And so this is a hallmark of a process, a convective process called double diffusive convection. And this thing itself is called a thermohaline staircase, and it's observed variously in other parts of the ocean. But we're really interested in it because I guess one of the key aspects of this problem is, the warm water is at depth. How does it get upwards towards the ice? And this process, it will act to mix and to transport heat very differently to other processes that we've talked and thought about. So this is a bit upsetting because this relates to a earlier slide that I removed. So we might skip it. But well, I guess just briefly to say, in the process, in the presence of sort of more energetic and more classic turbulent mixing, we might expect temperature and salinity properties to evolve along this particular line under an ice shelf. So this is a line where you put some water underneath an ice shelf and you do a bunch of melting and you mix in the meltwater, and the properties kind of evolve along that line in temperature and salinity space. So that's a neat way to to visualize the effects of meltwater beneath ice shelves. But for these particular profiles, you can see that we move on to this other line, and this is a line that's characteristic of this particular process. But yeah, I guess just another way of visualizing that mixing and heat transport are different for this particular process. So these are some really, really cool observations that aren't mine, and just one of those papers that you wish you'd written sort of thing. But it's contrasting these George VI, this environment, I guess, to another environment that we've talked about. So I think it's easier just to focus on the right-hand side plot. So when we were talking about the energetic well mixed condition, and I was drawing in, I guess, an analog to the Larsen C ice shelf, we had this great frictional boundary layer. And in a frictional boundary layer, the turbulence is related to the strength of the mean flow. So that's exactly what this plot is. So this is the mean flow on the bottom, and this is our turbulent velocity scale. And you can see, so these paler lines are those Larsen C observations, and you get this kind of, proportional relationship. But the observations that were presented in this paper about George VI show something completely different. So if we look at the darker lines down the bottom and the scatter, this is showing, I guess, that the friction velocity here is totally not correlated to the free stream flow. And so, again, this is another way of looking at, the fact that the processes driving the mixing are totally different. And it has really important implications for melting, because this relationship that I showed you before, it's really built for this type of frictional boundary layer, and it only makes sense in that kind of environment. So if U star is not proportional to U, then there's no way we expect this relationship to hold at all. So we also decided to investigate, well, that's it's actually the first bit of work I did, but we also wanted to investigate double diffusive convection beneath an ice shelf. And so, yeah, this is something, as I said, George VI ice shelf, and there's observations which suggest maybe near the grounding line of the Ross ice shelf this happens. So we took the same approach of doing these idealized simulations to investigate double diffusion and the formation of these thermohaline staircases. And that's what I'm showing on the left. So this is depth beneath our ice shelf, and this is time, this time in hours. And you can see in temperature up here, we form our first well mixed layer. And then at later time, we start forming another kind of cooler well mixed layer. And then if you're imaginative, there might be a third line down here. So it's a bit easier to see in the stratification, which is below. So what these blue colors, by the way, in the stratification mean is that unstable stratification, and that's an indicator of convection. So, and just because it's nice to visually compare with what I showed you before, these are the temperature and salinity profiles that were evolving over time. Okay, but yeah, so we spent a lot of time talking about how meltwater is affecting the turbulence beneath the ice in our earlier scenario. So, and I said many times that meltwater is buoyant. So how on earth do we get convection if the meltwater is lighter than the ambient ocean? Well, it's not just light, it is specifically cold and fresh. And so what that means is that near the ice, I've got to bring this all out, yeah. So near the ice, we have this scenario where actually, because we're so close to the ice, we can't really have turbulence yet. The ice itself is in the way. And so in terms of what's transporting heat and salt, actually molecular diffusion is doing all the work. And I'm not sure if this is common knowledge, but heat diffuses a lot more quickly than salt, sort of by a factor of 100. So what that means is if we have our ice up here and we do some melting, we have a situation where we're growing these diffusive boundary layers, so more boundary layers within our overall boundary layer. And we have one for salt, which is not growing very quickly. And then we have one for heat, which is growing much more quickly. And so in this scenario, we have cold above warm. And so this region in between these two boundary layers is somewhere where the water is being cooled, but hasn't yet been freshened. So this region up here is really strongly stratified, but this region here can actually become unstable in terms of the density gradient, and then we start to get convection. So that's the mechanism behind this diffusive convective process. Oh yeah, and you can sort of see these boundary layers up here in this figure on the left. So what does this mean for melting? All right. So on the right-hand side, I'm showing from a bunch of our diffusive convective experiments. And sorry to use the words double diffusive convection and diffusive convection interchangeably, but anyway. So this is the melt rate, and this is what's happening as a function of time. And you can see that the melt rate is always decreasing, and it has this relationship to time. It goes as t to the -1/2. So this, I guess, in stark contrast to the other scenarios we talked about, where melting was proportional to these expressions, it wasn't a function of time, and so this expression is sort of a steady state expression, whereas here we have a melt rate that's evolving in time. So the melting is time dependent, and that also means that heat flux, which we relied upon to drive convection, is also time dependent. And so what that means is that the strength of the convection is decreasing over time. So here, what I'm showing in the color is the amount of time for which this particular process occurs. So we're talking up here, like 1 hour, 100 hours, for example. And how that varies as we go from colder to warmer conditions, and how that varies as we go from less energetic to more energetic conditions. So yeah, so the take home from this particular bit is that if we expect this process to occur beneath ice shelves, but if you're in a scenario where the flow is quite energetic or it's quite cold, it might occur, but it might only occur for, say, a minute before the fluxes aren't strong enough to actually dominate the flow anymore. Whereas if you're at very warm conditions and quite sort of quiescent conditions, so this is about where we were for those Georgia 6 observations that I showed, you expect to see this process occur, and you expect it to sort of continue for a long time. So one thing I wanted to say about the melting, which I didn't get a chance to in this particular scenario, is the fact that it's time dependent is a real pain if we want to include it in sort of regional and large scale sort of circumantarctic ocean models, because yeah, it's not straightforward, I guess, how you would include a time dependent process in a model like that. Okay. Sorry, I hope no one's as exhausted as me, because I'm really exhausted. So yeah, so I guess the bit that we added to the puzzle here is that if we move to even warmer or more quiescent, less energetic conditions, we get this totally new process occurring called double diffusive convection. So I spent a lot of time talking about how meltwater suppresses turbulence, but in this scenario, you can actually derive turbulence, due to the meltwater. And melting in this regime is dependent on time, which makes it inherently difficult to parameterize. And yeah, this process could be short-lived or long-lived, depending on the cavity environment that you're in. Okay. So yeah, I wanted to, I guess, lay out some. Oh wow, I've been talking for a long time. I wanted to lay out some I guess, challenges and some possible regions for possible topics for future work. So I guess firstly, incorporating these different melting regimes into new parameterizations for the ocean models. Yeah, I don't need to rehash that. Oh, and this is my schematic. So you take all the physics in my box and poke it in here. I think that's how you build a parameterization. Sort of integrate what we understand about this scenario where we're beneath mostly flat ice with that convective type melting that I described earlier. So yeah, I mean, a big caveat to this is that those effects that I described where buoyancy was inhibiting the turbulence and decreasing the melt rate are very much results that should just hold for quite flat ice, because as soon as you start to get a slope, that buoyancy will drive the flow. So yeah, understanding where the cutoffs in terms of slope and what process is dominant is a big area that people are starting to work on, but there's a heap to do there. Oh yes, that's the picture that goes along with it. Another big one is incorporating the effects of roughness of the ice face and topography on the ice face, because basically we expect roughness, so this type of featuring, if present on the base of the ice, to enhance the turbulence. And we also see things like these terraces and other kind of channel type formations, and so we expect interactions between the flow, the melting, and the topography, and feedbacks there, right? Because yeah, the melting can actually generate these features. And then finally, a lot of other really interesting processes. So this has all been the steady flows, but I'm doing a little bit of work with tides and plan to do more with tides, as well as internal waves. And so that's quite interesting, I guess, because we know that on slopes, internal waves can, drive elevated turbulence, and the ice-ocean interface is sloping and very sensitive to turbulence. So yeah, that's one thing that I'm sort of planning on working on during this position, I think. And yeah, so this is some of the current work that's looking at the tidal-driven melting, and if there's anything of interest, I guess, in there. Yeah, so to flag that, yeah, these are things I'm thinking about working on and very interested to work with other people on in some capacity, especially the top one, since, actually parameterizing or including parameterizations in specific models, I haven't worked with many large scale models. So yes, yeah, and equally, if any of my expertise seems appropriate, I'd love to work with any students that you might be thinking of hiring through ACEAS. So feel free to reach out to me if you would like a co-supervisor with my skill set. That's my plug. And if I haven't bored you or I've totally confused you, you can read about these things in these papers. And thanks very much to Nathan and Ben, who supervised my PhD, and these guys who co-authored these papers, and Sue and Felicity, who read my things and handed me tissues. Yeah. Oh yeah. I don't know why George just got that. Thanks.
Now, we'll just start off with the one question that's two questions now. Can you see those? You want me to show you?
Oh.
Just read them out.
Sure.
Those ones. Can you see that?
Yeah, so Laurie Padman asks, when gamma T decreases, so that's our transfer coefficient, with a warming ocean, does the overall heat flux still increase, just not as fast as you'd expect? Yeah, exactly, Laurie. So it's kind of a relative effect. So it's just if you would consider a maximum possible melt rate, and then it's sort of a decrease relative to that. It just seems to be the most sensible way to explain it, but yeah.
And then Rob.
Oh.
That's also really big.
Rob says, thanks, Maddie. what is the influence of sea ice formation and melt, etc. That's what I thought I could ask you, Rob. Yeah, I guess maybe, this is all very much from the perspective of if someone tells me what are the properties of the water that makes it into the cavity, I'd like to then tell them the melt rate. As to what drives the changes in those water masses on seasonal or interannual timescales, yeah, that's that's a question I'm interested in, but not one that I specifically worked on. Yes.
Thanks, Madi. That was an amazing tour of what you've been up to. I was interested in your comment about working towards parameterizations in larger scale models, and I just wondered, is that pathway clear? Are there steps that you can take or hand to somebody else, and how long does it take to get there?
There's some short-term, I think there's some quick improvement steps that I understand how they would work. Modifications to some of those parameters that already live in there, like that gamete that I was talking about. But one of the problems, I think, is that there's not really knowledge in the parameterizations of the thickness of the boundary layer. And so those things that I talked about, like that the boundary layer thinning or that insulating effect, it's not obvious how you would include those effects in the current generation of parameterizations. So yes, I think that I need to talk to someone smarter about boundary layer parameterizations to work out actually how to do that, because that is more of like a reinventing the wheel a little bit. So instead of just saying, we know the properties at the top grid cell, we're going to predict the melt rate, we want to actually say, based on these properties, we predict this profile of fluxes, and based on that, we'll predict the melt rate, if that makes sense. So yeah, there's probably a month or two for could be some quick changes. I don't know actually, it could be way longer than that. And then sort of a decent sized project to make the larger changes. And I have some ideas about the pathway for that, but not ones that need airing to to smart people. Yeah.
And we've got Roland raising his hand online. Let's see. Go ahead, Roland.
Hi. Two questions which have been forming in my mind, which appeared not surprisingly in your challenges for future work. The first one is, one would expect that there would be some characteristic relationship that would tell you when slope was going to undermine your flat ice regime. The other question was in terms of the roughness, these typical patterns that one sees in field observations, which tend to suggest that there's a characteristic length scale for these dimpled surfaces. And have you looked at whether there's an instability to that sort of surface patterning, even in the overall flat case?
Yeah, I haven't looked at that. Yeah, so I guess for your roughness question, yeah, I haven't looked just to say, yeah, what are the main length scales in that melt rate pattern, and could they, I guess, feed back on themselves? Because I know someone has done Louis Storm has done some work, like, with an actually evolving interface to look at how it might evolve under different scenarios. But I haven't really looked at that with this work. And yeah, so with respect to the observations, like lots of that dimpling that I showed is actually, I think, from more vertical ice. And I'm sort of wondering if that might be more of a convective sort of melting feature that you get, because yeah, some of the observations beneath ice shelves have actually been totally flat. You can't really see any of those features. So it's not necessarily clear to me what the, whether it's expected to be dimpled in lots of sites or not. I think it's one of those things that really needs observations. Not that you could really hope to get like very good coverage, and yet seeing as it's possible that the features are related to the flow and to the melt, conditions and regime, you would expect it to be quite spatially variable and possibly also temporally variable.
Yeah, well, I mean, you see that the scalloped pattern often associated with icebergs, where clearly there has been a substantial slope, but I guess it's not obvious whether the important thing was simply a vertical aspect to the flow or the speed of the flow along the interface, which again is going to potentially be higher in those steep cases, but which could certainly be explored simply by driving your flat ice system faster. And certainly, I mean, even if you have an evolving interface, my suspicion is that, that potentially if you don't provoke a breaking of a translational symmetry like that by putting in some initial roughness, you might find that the system doesn't spontaneously produce it. Anyway, thank you.
Thanks, Roland.
According to the meeting reminder.
Okay.
So
Yeah.
do you want to wrap up?
Just thank you so much. It's so nice to get the long version rather than the 10-minute version. I understood that one a lot better. So thank you. That was a great job.
Thanks, man.
Thank you.